So I did have some communication online asking me what happens next year. Guessing incorrectly that the follow-up module would be CS203. Right. The number on the big end is the year number. That's the 1 for this and 2 for that. The number on the little end is random. They're just, they're numbered in the order in which we made them up. So CS203 is something completely different. The follow-on from CS105 is CS207, and the follow-on from this module, CS103, is CS208, which is called Logic and Algorithms. And since we've encountered a bit of logic and some stuff, it's taught by Bob Atke, who popped up in our first lecture, just by way of telling you that that we do talk to each other, and he expects you to remember the things I've taught you. But also, in semester 2 of second year, you will have a module called CS260 Functional Thinking, where the kinds of programming that we've been doing you'll do a lot more of that. So it's almost like we talk to each other and try and plan a sort of joined up experience for you. I realize that might be kind of worrying that we're in a conspiracy to cause education, but there you are. You're just going to have to live with it. So anyway, this lecture is going to be, we're going to kind of be a bit hybrid. That's why we've got pens and paper and a document camera and stuff. But I just wanted to kind of start by way of achieving closure with where we were going with Brzozowski. So if you remember, the idea is that given a regular expression and the first symbol in the input, we want to compute the regular expression that the rest of the input has to match if the whole of the input, including the first character, is to match the regular expression you first thought of. So we've got that, if we're already dead, we stay dead. If we don't want any input, we become dead. If we're asking for a particular symbol, it better be the one we've got. And then we preserve or. Do you notice we preserve fail, we preserve or? So we're mapping kind of 0 to 0 and plus to plus. And then for Q then R, we actually screwed this up last week in a very, very subtle way. We wrote everything here except these outer parentheses. And the default grouping that ask gives just groups them to the left. So we actually wrote the wrong formula. And that only came out when I was doing the proof to get stuff ready for the tutorials. So that's embarrassing. But it also shows the importance of actually doing the proof because it's very easy to not put brackets in the right place. And, if the machine says, oh, yeah, fine, I can do something with that, but it's completely wrong, you're going to come a cropper. So that was a nice little lesson for me.
So it's good. It's a good reminder that if you're wondering if you should put brackets in, then you should put brackets in.
Yes. Yeah. So we left on a cliffhanger. We hadn't done then, and we hadn't done star. Okay. So star is nice and easy, right? We know that if star like something non-empty, then it must have unrolled at least once, which means that the first of the sequence, now we know it's a non-empty sequence of R's, must have liked the input, and correspondingly, the rest of the first R is accounted for by the Berzovsky derivative of R, and then we've got all the rest of the R's. So that's the kind of explanation, roughly speaking, there. Meanwhile, for the case of Q then R, well, what do? You got to figure out whether Q at the input or R at the input. So you ask, how did Q then R match this input? And you find out that it was splits into Y's and Z's. And what we really need to know is whether Y's is empty or not. If Y's is empty, then R at the input and Q at nothing. If Y's is non-empty, then the Q at the input and the Berzovsky derivative gives you the rest of the Q. So it's lots of list hacking. It's sort of a bit scrappy, but conceptually not too intimidating, I hope. Yeah, same logic goes both ways. So we thought, since we got as far as, this bottom line, yeah, that's nice that, we've got a relation, big L likes, that that specifies what regular expressions match. And we've got a program that we not only claim decides liking, but we've actually proven that it decides liking. So correspondingly, the usual thing to do at this point is collapse in a heap, exhausted, but moderately happy. Very occasionally, it's kind of gratifying to do something like test likes. What should we have? I know what we shall have. We shall have sim b, then star of sim a, then sim a. And then we're going to feed in b, a, nil, spelt correctly. And that's true. But if we give it only 1a, we find it's we get false. So there we go. And I don't know how you feel, but it's a perverse aspect of the human condition that we are somehow more satisfied by seeing this program actually working on 2 examples out of the infinitely many examples we could possibly try than it is to have a formal correctness proof for the whole thing. I don't know whether, proving that it actually works is nothing compared to watching it actually work. I mean, it's kind of funny like that. So anyway, I will make sure that this stuff and the story about it all arrives on a website sometime soon. But now I realize that if we want to switch to the document camera, we're going to need to do something slightly clever with, well, we're going to want the document camera on that one.
Yeah.
So in fact, we probably want the document camera on both. I think we're probably done with technology for at least for the time being.
At which point you should actually stop sharing.
Yes, I should stop sharing so that Zoom people get a kind of slightly trans flag stripy view at a funny angle of the screen. Okay, now sensible people have a sacrificial base plate for the paper. Right. I hope this is enough paper. I think I've got some more paper in this envelope along with, yes, I do. So that's, we'll be fine. Okay. So I guess we should have an example. In fact, we should have the example we just had.
Yeah.
Right. So today we're going to teach you to draw some funny little pictures, which are more formally known as finite automata. So I'm going to draw a picture with 3 blobs. You don't have 5pence, do you? I don't know. You don't have a 5p piece or something like that. No, nobody has money anymore.
I'll give you £10 if you want.
No, that's useless. No, I need a small amount of money. A small round amount of money. Right. So these little black circles are called states. This is a picture of a machine. The machine has finitely many states, and at any given time, it is in one of those states. Okay. But the machine makes going should be green, I think. The machine makes transitions when it receives input. So what I do is I draw a green arrow and I label it with something in the alphabet. I'm going to label this one with a B. So what that means is, so the machine processes a sequence of inputs that are symbols coming from some alphabet. Ring any bells? Right, so what we're saying here is that if the machine is in this state and a B arrives, we move to this state and absorb the B. Okay. I'm going to draw another arrow. I'm going to label this one with an A. So if we're in this state and an A arrives, we'll move to this state. I'll draw arrow back there with an A. So we see if we're here and we get an A, we move to here. If we get then another A, we go back to here, and so on. Okay, so we're nearly at the description of the whole process. There's just 2 pieces of information missing. We need to know where to start, and we do that by just drawing an arrow in from empty space. And we need to know which of the states are happy states. So we can label 0 or more of the states as accepting, and we usually do that by drawing an extra extra ring around them. So if we end up in this state, we win. So if it's like, which state are we in when the input stops? If we're in an accepting state, then we're happy. If we're not in an accepting state, then we're sad. So you can see that this machine will accept the input. What? Okay, no, that's, I see why that's backwards. This will accept the input if the first symbol in the input is a B, and following that, an even, possibly 0, number of A's. No C's allowed, no B's allowed anywhere else but the beginning, even number of A's. So if we get BAA, we'll go BAA and win. If we get just BA, we'll go BA, and we're not in an accepting state, so we lose. Does that make sense?
So Connor, what does the machine do if it gets an A in the beginning?
Right. Well, then that's an excellent question. So strictly speaking, we ought to say what happens for every input, every possible input in every possible state, right? If you remember, that's how we wrote the likes function. We had a function that said what state we're in, how to make progress from a state and a symbol to the next state. So we haven't written a function here because we haven't said what to do with A or C here and anything other than A there. So the way we can complete that is that there's a secret extra state that I haven't drawn in the picture. Draw it big. It's a trap. And what happens is that anything we left out, anything that's missing, sends you into the trap. And once you're in the trap, you can't get out of the trap, and the trap is not accepting. So that's how we make what's called the transition function total, like adding this extra state. But in terms of drawing a picture of the machine, which is readable by humans, this extra brown stuff doesn't really tell us anything we couldn't figure out for ourselves. So we usually leave it out. But we should understand that when we work formally, there is an extra state, and we do say what happens for every combination of a state and an input. Okay.
So this means that if we're only drawing the thing without the brown thing, if we're ever in a state and we see an input with no corresponding outgoing arrow, right? That just means we lost. We're not going to accept this input.
Yes.
Which has the same effect as moving to the trap and then just moving around until the input stops.
Right. So I'm going to just label this picture. With the corresponding regular expression. Okay. So we give a chance for our folk to have a go.
Yep.
Right.
I'll take a picture of this.
Please do. Right. So I'll give you a few minutes to see if you can draw me a diagram for an automaton that will recognize that. So I realize that expecting you to have the ability to to have paper, a writing implement, and the ability to use them might be a bit much to ask of the COVID generation. But we'll give you a couple of minutes to think about that. And then I'll get Fred to do it. We're going to take advantage of this short pause and the fact that you're doing the next bit in the solution to this to nip out for a moment.
Okay, how are you getting on? Should we do it together? So, okay. So let's see if we can do this. So the way I would think about this is that I see the star as kind of the outermost thing. But in order to construct an automaton for the star, I'm going to construct an automaton for the thing inside the star, and then at the end, where the thing inside would accept, I'm just going to loop back to the beginning again, right? Because that means I can go around this loop as many times as I want. So I guess I better start with some kind of state. Okay. And then I look at the thing inside. Well, I see that I definitely want to read an A. And then after that, I'm happy with either a B or a C, right? But I'm going to start with an A. I'm going to construct another state and say that if I see an A, then I will move from my first state to my second one, right? And then here, I'm going to be happy if I see a B or a C. So I'm going to construct another state. And no one says I'm not allowed to have more than one arrow going out of my same thing. So I can say, well, if I see a B, then I'm going to progress. And if I see a C, then I'm also going to go to this state. I don't really care which one I saw. I'm happy with either one, and I'm going to end up in the same situation, right? So like Connor did with a trap just now, we also usually do a shorthand for saying I'm happy with either one of these by just writing B, C on one arrow, right? But if you want to be really clear that there's two options. You could draw two arrows. And of course, I could have the case where the B goes to one state and the C goes to another state, right? Okay. So that's the end of the thing inside, right? I'm happy if I see an A, and then if I see a B or a C, and then I want to go back to the beginning again. So I could draw that like this. But then I'm tempted to draw an arrow back to the beginning, right? But then I would have to put a label on this arrow, which is not very nice. So probably what I should have done is I should have drawn these two B and C arrows going back to the beginning instead, right? So that would be one way to do it. If I don't want to do that, I could actually kind of make the trip back again, right? So I could say, well, if I get an A from here, and then if I get a B or a C from here, then I'm back and I'm happy, right? But I also need to say, what are the accepting states? So the star says I'm happy if I get no input. So if I go around 0 times, right? So actually my initial state is accepting. And if I get to here, then I've been through it once, right? So this one is accepting. But these two states, I've only seen an A, but I haven't seen a B or a C yet, right? So I'm not happy here because that's not matching this expression, because this says I should get an A and then a B or a C, and I can do this as many times as I want. But if I only get an A, then that's wrong, right? So I think this kind of works. Let's try it out. What's your favorite string on that matches this? A, B, A, C, right? So if I get an A, then I'll move here. If I get a B, then I move here. If I then get an A, then I move here. And if I get a C, I move back here, and that's accepting, right? If I get AA, what happens then? So then I make an A, and then there is no explicit label with an A on it. So that means we're moving to the secret trap state, right? So we are not accepting here. So we are accepting A, B, A, C, but we are not accepting AA. So that seems to match. So one thing we can see from this is that there's many ways to draw an automaton for the same regular expression, right? So like we said, another way to do it here would be to say, okay, I have my initial state, then I have my other state. If I see an A, then I'm going to move over here. And if I see a B or a C, then I'm going to move back to my initial state. And with this automaton, starting here, then we only have one accepting state, right? Which is the initial one. And in some sense, this is a better automaton, right? Because it's just more compactly described. But it accepts the same language as this one. So you could ask, given an automaton, is there a better one that does the job just as well, right? A smaller one that does the job just as well. And you could ask if this is decidable or not.
Indeed. I guess we should actually write down the definition.
Yeah.
Um,
Take a picture of that.
We do. So a So what is a deterministic finite automaton, or DFA, as everyone calls them, is given by a finite type S of states a finite type A of symbols a function in how did we do it? We do S to A to S. How the machine reacts to input. A function.
Need to go up.
In S to bit tells you whether we're happy to stop and a start state. S. That are we all zoom out a little bit? Obviously, writing on a piece of paper is not a very good way to upload things to the internet, but I probably can manage to type it out again. Okay, so those are the ingredients. And what makes it deterministic? So deterministic means does things in a predictable way. So that's to say, this is a function for any given combination of a state and a symbol in the alphabet. There's exactly one state that we'll end up in. There's no choice about it. It's the same every time. And there's no random behavior.
And it's a function in the input-output sense, right? It's not a Java function which looks at the current clock and decides to do one thing on a Monday, another thing on a Tuesday. Right?
Yes. In CS103, the notion of function is the mathematical notion of function, which is something which connects every possible input to exactly one possible output in a way that is consistent every time the function is used. So no No giving a different answer when it's full moon. Right. So that's the definition. And we already saw, right? So you can see also, if those of you who do CS106 or did CS106 last semester, you might remember building some circuits that used D flip-flops. When you've got finitely many flip-flops, you've got a finite amount of memory. And these are machines that have a finite amount of memory, right? If you've got some number of things that can remember a bit, then you've got 2 to the power of that number of possible states. And likewise, we want the alphabet to be finite because, well, you need to be able to transmit it over finite resources, like in a finite amount of time or over kind of finitely many wires. So this is basically, these things are the machines we can actually manufacture. And so this is, these are real computers. Yeah, this thing is a deterministic finite automaton. Even when it pretends to do random things, it doesn't. All the randomness is fake. But yeah, of course, it's the nature of these things that once they get sufficiently big, knowing that they're finite doesn't actually help. It's much the same way that mathematicians, and especially mathematicians who work with computers, have a deep aversion to numbers larger than 2. Counting goes 0, 1, 2. Why am I doing this? Yes. And yeah, it's you know, if our trade union shop steward catches us using numbers bigger than 2, we get in trouble. We're taking somebody else's work. Okay. So you can bet that I'm going to give several marks away for just being able to behave like a machine. Right. How are we doing?
Is it worth actually taking a picture and saying exactly how it corresponds to the definition?
Yes. Okay. So here we go. See if I can fit enough things on one page. Right. So finite type S of states. You can see that formally this automaton has 4 states. The 3 I originally drew and the trap. Okay. So that's the state set. An alphabet of symbols. That's your A, B, C. A function taking an S and an A and giving an S. You can see for each state, there's exactly 1 arrow coming out of it corresponding to each possible symbol, pointing to another state. We need a function from S to bit, and that's the one. So you're allowed to draw more than 1 ring around a state. So
as we did in this example.
Yes, each state separately you choose whether it's accepting or not. So here it happens to be that this one is accepting and the other 3 are not. So that's the function, and then a start state, that's what the free floating arrow points to, and that has to be just 1. Okay, So that is the notion of a deterministic finite automaton.
And it also works the other way around, right? If Connor gives me a finite type of states and a finite type of symbols and a function like this, then I can just draw a picture corresponding to this, right? So I'm going to draw all of the finite states, and then I'm going to put in the arrows if the function tells me to put in the arrows, right? And then I'm going to use this function to draw the double lines around some of my states. Just running the function on all of the states. If it returns true, then I draw a double line. If it returns false, I don't, right? And then finally, I draw an arrow for the given initial state. So the picture and the formal definition really is the same thing.
Right. And so now we figure out, given this story, what Brzozowski is actually up to. Brzozowski is turning a regular expression into an automaton just in time. So taking the regular expression and figuring out how it transitions as, you know, in real time as the data turn up. You know, where do we go next? Yeah, and it is the case that, okay, strictly speaking, there are infinitely many regular expressions. So if you want to think of the regular expression state as being if you want to think of states as being the regular expressions themselves, then that's not a finite set of states. But if you especially if you simplify the regular expressions that you get by the usual algebraic laws, you will find that as you repeatedly do Brzozowski's derivative on a regular expression, you will only use finitely many regular expressions. So it does actually give you an automaton, which is good to know. We will come back to that in a bit. Do you think it's half time?
Yes. Yeah.
Yeah. This is a good place to take a break. So let's take 10 and be back at 2 minutes 2.
Recording?
We should pause the recording. Hello again, folks. As good as it gets. So we're going to tell you about a variation on the theme of DFAs, which is a thing called a non-deterministic finite automaton. And I'm just going to make one up out of nothing. Because, so let's start with an example.
You start recording again?
I did start recording again. So I'm just gonna draw some states in various places, and I'm going to pick one of them to be a starting state, and let's have two of them being accepting. So far, the same, finitely many states, finite alphabet. Some states are accepting. There's a start state. What's different is that the transitions, as the name non-deterministic suggests, do not have to be deterministic at all. So for example, I'm going to, I should have drawn those in green, shouldn't I? Never mind, maybe
for non-deterministic.
Yes, maybe we're being blue, right? So for example, I'm going to label this one A, B, and label this one A, C. What does that mean? It means that if we're in this state and a B comes along, we definitely go here. If a C comes along, we definitely go here. If an A comes along, we might do either. So we're now talking about multiple possibilities. Okay. And let me just fill in a few more of these things. Let me just draw lots of arrows and then decide what to put on them. Something like that. Let's label this one B, C. That's going to be an A or a C. This one, let's say, is A, B, C. And this one is just, well, this one's just going to be a B. And this one is going to be, this is the other surprising thing, epsilon. Right. So the arrows labeled with epsilon are transitions the machine can spontaneously make without taking in any input at all. So if we're here, then the machine is allowed to say, I don't like it here anymore, I'm going there, without receiving any input.
So I'm thinking of epsilon standing for empty, because it's taking in the empty string and then it moves, right?
Yes.
So it's eating all of the empty string, which leaves the input as it was, and then.
So you're allowed to give multiple possibilities for what to do when eating 0 or 1 input. Okay, so this is an example. I mean, we could just sort of play a game. I mean, so this thing will accept A in 2 possible ways. It will accept, well, it will accept B, it will accept C. What else will it accept? It will accept AB, but it will not accept BA. It will accept
So Connor, what does it mean for it to accept something now? Because maybe there's one way to go to an accepting state and another way to go to a non-accepting state.
Right, so we take the sunny view. If there is any way to achieve acceptance, right? So when I was saying that multiple things can happen, but if there's any way to accept the input is accepted. So it's not like, you know, some perfectly acceptable input turns up and you get unlucky and it's rejected. This machine is really supposed to, given the things it's allowed to do, it's supposed to try them all. And if anything works, the whole thing works. So,
for example, if it takes CC, right? Then the first C, we have no choice. We have to move to this state. But then there's 2 ways to move with the C. We could either go this way or we could go that way. But because it's possible to go into an accepting state, this machine is going to accept CC. We only need one good path. We don't need all the paths to be good.
Yes, and we can see this machine will accept A followed by any number of B's and C's, because maybe we get an A, we go here, we get a B, we go there, but then we can come back here immediately. So there's that's the epsilon transition in action. And of course, you can do things which look unhelpful, like that. Right. Let me just draw a line. This is useless but harmless. That's to say, because of our you win if anything works. Chucking in something that definitely doesn't work doesn't hurt you. Okay. I suppose we should write down a.
Yeah, maybe can I say one more thing?
Please
So
do.
in our previous definition, we had exactly one starting state, right? But now if we have these epsilon transitions, then if we want more than one starting state, we can always make a new starting state, and then we just make epsilon transitions to all the states we really want to start from, right? So for that reason, sometimes in a non-deterministic automata, we also allow a finite number of starting states. And it's the same deal. If you can start from one of the states and get to some accepting state, then we're happy, right? You don't have to be able to do it from all the starting states. But this is sometimes quite useful when you're trying to write down an automaton and you want to have two possibilities, for example, then you could start from one state or the other state.
Yes. And dually, given we have epsilon transitions, we could arrange to have exactly, or rather, if we want to have exactly one accepting state, then we just make a new state, which is like kind of the end stop. We make epsilon transitions from all the accepting states to that state. So you can play it that way if you want. Okay. Time is quite a precious resource. So I'm going to write a non-deterministic finite automaton. Sometimes known as an NFA, is given by a finite S A relation, so the sort of thing you can define using prop in ask, which tells you how to get from some state to some other state when you receive an input. Relation that says which states are related by epsilon transitions and then a start state. And I'm going to say 1. Well, no, okay. A function S to bit for which states accept. Right. So, although as a cardiac outpatient and a trade unionist, I don't like creating stress and tension in the workplace. I think we can allow ourselves briefly a small mystery. Right, it's perfectly clear that you can take any deterministic, so that the definition of non-deterministic finite automaton includes all of the deterministic ones, right? Because you could turn a function into a relation, and you just, the fact that you're allowed epsilon transitions doesn't mean you have to have any. So certainly all the DFAs count as NFAs, but there are some NFAs. NFAs give you extra stuff, extra ways you can process the input. So the mystery I want you to think about in the back of your mind as we truck on, which I hope we will resolve by 11 o'clock, is whether NFAs actually give you any extra power. Is there anything you can do with an NFA? I mean, they can process stuff in different ways, but that may but the question is, are there matching processes that you can do with an NFA that you can't do with a DFA? So have we bought ourselves anything extra in terms of power, by chucking in this extra stuff? That's what I'd like you to enjoy worrying about as we go along. But we'll.
So maybe should I do a very small example?
Yeah, yeah.
So let's take a very simple NFA.
No, don't overwrite. Right. See this? This is why we have a base plate. Yes.
So let's just do something very simple, and then we can think about it, right? So I'm going to have 3 states. If I see an A, then I'm going to non-deterministically decide if I'm going left or right. I'm going to start here, and this is an accepting state. Right? So this is an NFA, but it's not a DFA, right? Because A, I could either go here or I could go there. But of course, there is a DFA that does the same job, right? Which is this one. So it's not the case that every NFA is a DFA. That's not true. But in this case, I could find a DFA that works just as well, right? So the question is, can you do this in general or not? This was a very simple case, but we managed to kind of remove the non-determinism, right? In a very simple way in this case. I don't think it's going to work this easily in all cases, but at least the question makes sense. Right? You could maybe imagine that you have some non-deterministic choices, but somehow you could set things up so that you find a possibly more complicated automaton that does the same thing without non-determinism. So I guess that's what we want you to think about. I lost the pen.
It's on the floor.
Okay.
Let's have a recap. Right, yes. So we want that, and you will that one as well. Okay. So you may have noticed that some of the automata we have drawn so far, we have also labeled them with the same page also had a regular expression on them that was talking about the same notion of acceptable symbols. So that might raise the question of whether it's possible to come up with an automaton given a regular expression. So if you give us the regular expression, can we, tinker about in the shed for a bit and then wheel out an automaton that does the job of testing whether that regular expression accepts a given sequence of symbols. And so far, we have some anecdotal reason to believe that is so, but we've seen some examples of it, but how would we check? Well, I'm going to propose that we play a game of let's give an inductive proof that for every regular expression we can build a non-deterministic finite automaton that does it. Right. And this is the real reason why we're bothered with non-deterministic finite automata, is because they're much, much easier to plug together. Okay. So here's how it goes. I guess we're going to take turns to do the cases of the proof. I'll start. So, fail or zero, as it's sometimes known. Right. There has to be a start state but it's not acceptable. Right, your go.
And if you wanted, you could, if we had this secret trap state, right? In this particular case, you could just make the start state the trap.
Yeah, well, because we're dealing with a relation, we don't even need a trap state.
Okay, let's do an NFA for null. Right. Okay, so this should be the thing that accepts exactly the empty string, right? So I'm going to have two states. And the start state. And if I see anything at all, I'm going to move to my other state. And I'm only going to be happy if I never move to my other state. Right. So here I put my whole alphabet, right?
Yeah, I mean, you don't even need that, but except that I've actually screwed up. I didn't tell you all the rules of the game, and I broke one of them myself. So let me get this right. That we should give ourselves an extra restriction, because that will help, right? That each of these things should have one start state and one accepting state. So so one designated start state, one designated accepting state. So I'm just going to finish my example by doing that. There's an accepting state. You just can't get there. Right. Okay. So that means each of these things is going to have one beginning and one end. Okay. So we've got fail and null. I guess the next thing we need is an NFA for a single symbol. I think that can just about fit on the bottom of the page.
You move the page up.
Okay. Two states. One designated start state. One accepting state. One transition labeled by A. So there we go. That's our three base cases of the induction. We know how to build a one start state, one accepting state, NFA for fail, and for null, and for sim A. Now we've got three step cases to work through. So maybe we can take turns to be the supplier of the induction hypothesis. So an NFA for P or Q. P or Q, you might normally write. Okay, so I will give Fred some automaton which has a start state. Oh, I shouldn't have colored that in pink. I will color it in orange instead. Start state and an accepting state. And I will also chuck in an automaton that recognizes Q with a start state and an accepting state. And I want Fred to complete the job, to take those two components and make one that actually does P or Q.
Okay, so I'm going to make a new start state, and I'm going to make a new acceptance state. Let's record that. This is my start state. This is my accepting state. And then I'm going to make use of non-determinism to go from my new start state to whatever the start state of P is, and to whatever the start state of Q is. And I'm going to do this with an epsilon transition in each case. Right? So without consuming any input, I'm going to non-deterministically decide to move to P or to move to Q. And similarly, from the accepting state of P, I'm going to non-deterministically go with epsilon to my new accepting state and an epsilon from the same thing from Q. So some input arrives. I'm non-deterministically going this way or that way. Then I chuck it through P. If it reaches an accepting state, I'm going to move on to my real accepting state without consuming any more input. Right? And similarly for Q. And the non-determinism is going to take care of that. If P likes it, well, then I have a path here so that I like it. If Q likes it, then I have a path here that I like it. And if neither P or Q likes it, then there is no way for me to get from here to here.
Yes. So we should also emphasize once again that the non-determinism is what we call angelic. So that's to say, it is as if the machine automatically chooses the correct or a suitable path, if there is one, to make you happy, as opposed to a machine that is that vends either tea or coffee, and when you press the tea button, it said, "But I decided to make coffee," right? So yes, this is uh, this is a machine that will accept P's or Q's. It won't say to it, if you give it a P, it won't say, "But I decided I wanted a Q."
Another way to think about it is it just tries all the possibilities, right?
Yes.
And if one of them works, then we're happy.
Yes. Whereas there is such a thing as demonic non-determinism, where basically if there's a way to screw you up, you'll be screwed up. And so you got to know whether things are on your side. But I think Fred is going to set me a challenge.
So let's do the other way to plug two things together. So this one saying I'm happy with either one. Let's do first one and then the other, right? So let's see if we can build NFA for P and then Q. So again, we can assume that we have already built NFAs for the smaller pieces. So let's say there is one for P here, and there's one for Q here. I'll put them on top of each other
for convenience.
And we can assume that we have a designated starting state in P, and we have a designated starting state in Q, and we have a designated accepting state in each one of them. So now the job for Connor is to somehow plug these together so that overall it acts as P and then Q.
Okay. Well, so I want a P, then a Q. So what I'm going to do, I'm hoping you won't faint with amazement when I do this. I'm going to designate P's starting state to be the starting state. I'm going to designate Q's accepting state to be the accepting state. I am going to add a new transition from P's accepting state to Q's starting state, labeled with an epsilon. So this will be happy to start here, and if we get something which begins with a thing that P accepts, we will find ourselves here, and then we can spontaneously move to the start of a queue, consume a queue, and be happy if we're happy to stop at that point. So we've got as far as P, then Q.
You can kind of see why Connor insisted on having exactly one starting state and exactly one accepting state, right? You could do this if you had many accepting states, of course, but then you would have to go from every accepting state in P to every starting state in Q, and it would just be messy to draw it.
Yeah, but the fact that we've got epsilon transitions means it's fine to have one of each. That doesn't lose us anything. Okay, lots of pictures to right. So okay, we've got one thing to go. NFA for star R star, as it's often written. And I will give Fred a ready-built automaton for R with a designated start state and a designated accepting state, and invite Fred to go loopy.
So this is kind of what we did in the example before, but except we didn't have NFAs, we had DFAs, right? But now we have an NFA, so now it's much easier to do this. Because what should the automaton for star R do? Well, we should be happy if we go around R 0 or more times, right? So I'm going to say that, well, my starting state is going to be the same as the starting state of R. But I'm going to move the accepting state to be that starting state, because I should be happy if I go around 0 times. And then I'm going to add in one transition from the accepting state back to the starting state. And I'm going to make this an epsilon transition. So again, if I'm get the empty input, the empty string, then I'm happy. I just stop immediately. If it's non-empty, then I'm going to move through R. I'm going to get to the finish, which is not the finish anymore, right? It's the finish of R, but my new accepting state is this one. But I'm going to move back with an epsilon to the starting state.
Okay, so that's pretty cool. We've covered all the ways of building regular expressions, showing how to build up the NFA the same way that we built up the regular expressions. We know that as long as our regular expressions have this inductive property, right? Remember, back in lecture 1, there was the property of numbers that no matter how many spuds there are in the number, you eventually get to the lemon. No matter, you can't keep taking regular expressions apart forever. You might work your way through some stars and some thens and some ors, but you will eventually get to a fail or a null or a sim. So that's a way of guaranteeing that we've covered the whole thing. We've built up from the basis. So that's an example of the power of induction. Some people tell you that induction is only about numbers, or they've only noticed induction being about numbers, but induction is really about structure of all sorts. Anything with the property that you can't keep taking it apart forever is going to give you induction as a method of proving, and a method of programming, and a method of reasoning.
Can I do this again? I just realized this is completely wrong.
Is it completely wrong?
You have to be a little bit more careful, because R could make a detour and get back to its starting state, right? Without actually going to its finishing state. In which case we would now accept it. Even though R didn't accept it. So I think we just have to move this out of R and make an epsilon transition.
You've lost me.
Let's say, maybe I'm wrong.
Yep.
Let's say this is my R.
Yep.
With an A moving back. If I now do what I said I would do, and make this my new starting state and this my accepting state, then I will accept AA, right? Even though R does not accept.
That's fair.
AA. So,
Okay.
so this doesn't work. This is wrong. I have to do instead. We just have to make our own new starting state, a new accepting state, and then an epsilon transition here, and make our epsilon transition here go back to the external state. Because otherwise, the internals of R could get in our way and make us accidentally go back. But now, the only way we can go around this loop is if we get to the accepting state of R and then make an epsilon transition.
Yeah. So thank you for the concrete counterexample. That's an important stylistic lesson is that if you want to convince somebody that something works, then you want to be as general as possible. If you want to convince somebody that something doesn't work, you should give a counterexample that's as small and specific as possible. You know, how to file a bug report, right? You know, okay.
Okay, sorry about that.
Well, you know, it's a teachable moment. Right. So where did that pink pen end up?
We have a pinkish one.
Right, but there's a cap with no pen. I think it went under there.
Right. Let's worry about it later.
Uh-huh. Ah, yes. Thank you very much. Okay, so we got as far as we've turned regular expressions into NFAs. We're still left with our mystery as to whether we can turn whether there's anything extra in NFAs, right? Suppose we didn't want an NFA. Suppose we actually wanted to turn a regular expression into a DFA. And we've got some kind of reason to believe that there is a deterministic process for matching a regular expression because we've built it with Brzezinski's derivative. So, the question we really need to get to is, okay, somebody gives you an NFA, can you make it deterministic? And you can do it with one weird trick.
I mean, if someone gives you a concrete NFA, then you can often be clever and do it, right? But it would be nice to know that it always works.
Well, I was going to ask you to give me an NFA with some number of states that is preferably not as big as that. At most 3.
At most 3 states. You know what that means, right? We're going to have 3 states.
Yeah.
Okay. I'm going to have starting states, 1 accepting states. Let's make it 2.
We keep on doing this. There's a whole gang of us who show up to lectures together and play constant pantomime games of dropping the other one in it. All the way to fourth year. So,
Okay, something like this.
that looks pretty good. Right. Okay. For my convenience, I am going to number these states. This is state 0. This is state 1. This is state 2. Now, I'm going to wish I had 2 document cameras. But maybe
Just to the side.
hustle that over there. Fold it out of the way. Hope I don't regret this decision. Right. I am going to make deterministic finite automaton, which instead of having 3 states, has 8 states. That's 2 to the power of 3. And I'm just going to write them in a big circle and hope. Actually, I'm not. I'm going to write them
Up, please.
up like this. And I'm going to number them in a slightly more lavender shade. 0, 1, 2, 3, 4, 5, 6, 7. What could possibly be going on? If you think about these numbers from 0 to 7 in binary, they're all 3-bit numbers. That's to say, there's a bit worth 2 to the 0, a bit worth 2 to the 1, and a bit worth 2 to the 2. So we can map between the states in this automaton and sets of states in this automaton. This is the empty set. These are the sets with just one state. 0, 1, 2 to the 2 to the 0, 2 to the 1, 2 to the 2. These ones contain exactly 2 states. So that's 0 and 1. That's 0 and 2, and this is 1 and 2. 0 and 1, 1 and 2, 2 and 0. And then this is all 3 of them. Okay. So now we play a game. We say, which are the starting states? And Fred's been kind and given me just one starting state. So if there were more, what would I do? Well, I would just point to the set of them. Okay, but we're starting in the 0 state. So 2 to the 0 is 1. So that means I'm going to start here. And I really hope I'm not going to mess this up. Okay. We are allowed to stop if we are either in the 0 state or the 1 state. So what do I do? Do I go for accepting anything with an intersection with 0 and 1? But yeah, what I'm going to do is model all the states I can possibly get to. Yeah, I think I do actually do it with any intersection. So I'm looking for so I accept if it's possible to get to something which has either 0 or 1. So that means the accepting states are this one and this one, but not that one, not that one. Then all three of all the rest are accepting. So these are the only bad states. This corresponds to being nowhere. This corresponds to being only in state 2. Okay, so let's see if we can figure it out. Suppose we're in state 0. If we get an A, where can we get to? What's the set of states we can get to? Well, we can get to state 1 and we can get to state 2. So the set of states we can get to from here is given by 2 to the 1 plus 2 to the 2. That's 6. So if we receive an A, we'll go here. So I need to figure out, okay, if we're not in any state, we can't go anywhere. True of life as well. Okay, let's just work through the base cases. If we are in state 1, well, okay, maybe I should finish off what happens with the other symbols. If we get a B, we're definitely going to this one. So there's a transition, label B goes that away. And there's a transition. Likewise, if we get a C, we're definitely going to state 2. So that's C. Okay. And then what happens next? I have to think about what happens if we're in state 1. Oops. I've cocked that up because there's an epsilon transition from state 1 to state 2. So in fact, this is wrong. If we get an A, we can actually end up anywhere. So this is wrong as well. If we get an A, we're going to state 7.
Because we could either go over an A to here, or we can go over an A to here, or we could go over an A and an epsilon. So we can't go back to here.
Okay, let me live theater. Let me just start drawing. A clean page contains no errors.
Bigger circles, maybe. And if I were you, Connor, I would just label these states with the sets they represent rather than binary.
Binary coding, right? So this is 0, 1, 2, 0, 1, 1, 2, 2, 0, and this is 0, 1, 2. Okay, let's play this game again. Right. From the empty set, we can't go anywhere. From the set containing only 0, when we get an A, we can end up in 1 or 2. And the same is true if we get a B, because if we get a B, we can go here and then use an epsilon transition to get there. So that's A and B. Okay, if we get a C, we're definitely going to 2. Okay. If we are in state 1, well, in fact, we know that we'll never be in state 1. But it's worth figuring out anyway. If we're in state 1 and we get an A, then we will end up in either state 1 or 2.
Oh, yes, 1, right? The only transition we directly can make out of 1 is the epsilon transition, and then out of 2, we can only make an A transition and get back to 1.
Yeah, but then we can do an epsilon again.
Ah, yes.
Yes.
Yep.
So
you're right.
So I end up, if I'm in state 1 and I get an A, I'm going to 1 or 2. If I get any other symbol from state 1, I'm screwed. If I'm in state 2 and I get an A, then I can go to 1, but that means I can also go to 2. So that's labeled with an A. And now I have to, I forgot to redraw the acceptances. Right. And I have to figure out what happens. But then if I'm in 0 or 1, and I get then where can I get to? I can get to if I get an A from 0 or 1, I'm going to 1 or 2. So there's an A there. If I get a B from 0 or 1, I'm also going to 1 or 2. And if I get a C from 0 or 1, then I can go to the only place I can possibly go to is 2. So I'm saying what's possible. Now I'm recording all the possibilities. That's the key thing. That's a bit of a nuisance of an arrow. Let's see. If I'm in 1 or 2, the only thing that can happen is I can get an A and go to 1 or 2. And if I'm in 0, 1 or 2, I can get, and I get an A, a B, or a C. Guess what, folks? We're definitely going to end up back in 0, 1, or 2. So we've now written a deterministic automaton whose job is to track all of the possibilities of the non-deterministic ones.
So you didn't do the 2 or 0 state.
Oh, yes. In 2 or 0, that's fair. Where can we get to? If we get an A, we can get to 1 or 2. So funny that. Another A. Is this right? This is not right. If we're in 0, 1, or 2, and we get a, if we get an A, we're still all over the place. We can get to anything. So that should be, that's right, that's an A. But no matter where we start from, if we get a B, we're going to 1 or 2. So that's a B. And the only place we could get to with a C, well, it's also a C. Because, no, if we get a C, the only place we can go to is 2. So let's get that right.
This is
also labeled with
also always what happens when you do these things.
Yes.
You end up with a mess.
Yes.
So if you want to do it, you make one, then you transcribe it on a nice piece of paper and it's readable.
Yeah. But yeah, so you're also witnessing a phenomenon where this is a job that's easy for a computer but hard for a human, because we have to remember all the fiddly details. But all we're doing is using states of the DFA that represent sets of states of the NFA to say, what are all the possibilities if this is the input we get? All right, looks like a good place to stop. Have a lovely weekend, and I'm sure our tutorial homework will be forthcoming at some point.